Now let's continue the second part of today's class, which is the main components of an operating system. If you remember previously, I talked about an operating system that is composed of 3 layers, including interface and then shells and then kernel. So the interface is the user interface, which is another program that is part of the operating system. And then we do have the shells and the kernels. The shells and the kernels in general are those layers of an operating system that performs tasks related to the operating system as a software and the hardware. In order for the operating system to communicate directly with the hardware level, it acts as the manager, if you remember, is the manager of or the controller of all the tasks that should be completed, as well as it's the interface between the user and the hardware. In order for the operating system to act as a manager, to control other managers, each one of those managers is responsible for a certain task that will execute those system calls or those kernels operations. Each one of those managers perform certain assignment, and we look to the operating system as the manager or the head or the controller of all of those sub-managers. We know that operating systems are very complex. We also know that operating system would need to manage different resources in a computer system. So each manager that the operating system will control, so this is the general manager. And it's at the end of the story, it's just a program that has three layers, including user interface and then shell and kernel. And I said shell and kernel in general, it will be divided into those 4 other managers. So we have a memory manager. Still, it's a program. So we do have a program that provide memory management. We have another program that provide process management, another program that does device management. And then finally, we have another program that provide file management. Operating system, we look at it as the program that controls or provide responsibility of managing those managers. Each of those manager itself is responsible for managing their own department. When I say like a department, that means their own area of assigned task. So for memory management, for example, it is only responsible for managing the memory. It doesn't do process management. For the process management, it's only responsible for process managing the processes. It doesn't do memory management. So each one of those is responsible for its own department or its own environment. We might see some communication or cooperation between those managers. And then the operating system is the main controller or the main manager or like the general manager that control all of these sub-managers or all of these several managers that work underneath the operating system. Recently, when we look at modern operating systems, they do have 4 managers, at least 4 managers. Do we see more? We do have another managers, especially when it comes to security issues related to real-time applications and distributed systems. But for a modern computer, we should have at least 4 components or 4 managers: the memory manager, the process manager, the device manager, and the file manager. So let's consider the main tasks of an operating system. And then after I'm going to talk about the base tasks of an operating system, I will go over the 4 managers and I will cover some details related to each one of those managers separately. So in order for us to design an operating system, and we need to write a code for it that will be executed first time, loaded to the RAM to be first run. And then once it is loaded, any request it could be sent to the operating system to execute or to complete a user task. There are some fundamental functions or tasks that the operating system, no matter what type of operating system is, it could be a multi-process operating system, multitask operating system, or a real-time operating system. There are basic functions that any modern operating system should perform. Based on those basic functions, we will address the 4 basic managers that work underneath the control of the operating system. The first function that an operating system would necessarily perform is file and folder management, in which an operating system would create a file structure. This would be created on the computer hard drive, at which we know that the data could be stored and easily retrieved. Also, the operating system would perform application management. So that would request the operating system to locate the application and load it into the primary location of the main memory, in other words, the RAM. Also, the operating system support or should support the built-in utility programs, because we understand that when we design an operating system, it should come with tools for maintenance and repairs. As I said before, these tools would identify where the problem exists, which files have been lost. They will be able to find those lost files. They will repair the damaged ones, and they do backups for your data. Also, one other basic function of operating system is to control the hardware. So operating system is mandatory to facilitate the access of the programs to the computer hardware. This will be done through the BIOS and also through other device drivers. Based on those main basic functionality, we would like to see or to visualize or to imagine an operating system as a big program is divided into 4 managers. One of them is responsible of managing the memory. Another one is responsible for managing the processes and how the processes are executed. A third one is responsible for managing the files, the file management system, how the files are managed using the operating systems. Also, how the devices or the hardware are managed. Let's start by the first one, which is the memory manager. So that means we are looking to a part of the operating system that is responsible of managing the main memory. When I'm talking about memory, I'm talking about the main memory, in other words, the RAM. One of the responsibility of a modern computer system is to manage memory. When I say memory managing, means resource allocation, like how to allocate the processes into the memory efficiently. Because we know that although the memory size of nowadays computers has actually increased in a very large scale, especially in the last few years, we also know that the programs or the applications also has increased in terms of size, and that means it needs a lot of processing, and it needs a lot of efficient consumption or allocation into the memory. So the operating system should take care of this efficiently and guarantee that when a process is executed, the memory is used efficiently. That means we need a part of the operating system that will manage the memory. With that being said, memory allocation should be managed to prevent any applications from running out of memory. So if you design an operating system that's not efficient enough to manage its own memory, that means you might end up to have no space in your memory, and you have lots of processes that are waiting online, and then your computer will take forever to execute those processes because the memory is running out of space, or we're running out of memory, and then we don't have enough allocation in the memory to execute those processes. That means your operating system is not efficient. So based on what type of memory management your operating system is performing, like is the operating system do monoprogramming, like just one program at a time, or the operating system does multi-programming, that means we have multiple processes that would like to execute it, the memory management is different. So handling one process at a time would need a simple memory management, while if you are handling multiple processes at a time, your memory management and allocation is slightly complicated as compared to the monoprogramming, or it needs more handling or smart handling of your memory to provide efficient management to the memory and the process allocation into your main memory. The second manager as a part of the operating system, which we will talk about it a lot in this semester, is the process manager. So process manager is another component or another sub-manager that is facilitated by the general operating system manager. And it is responsible for managing the processes. In other words, scheduling the processes. So when the process is in the memory, so now we do have a process comes in place, and now we have the memory, the process would like to be executed. That means would like the process to reside in a memory. Which process should be actually scheduled to reside in a memory? Like how would you decide on a process to reside in a memory? Because once a process in a memory or in the RAM, that means the process is ready to be executed. But the operating system receives many processes. How would you schedule the arrival of processes? How would you schedule the execution of the processes? That's where the process manager is responsible for. So the process manager uses two schedulers. The first one is called the job scheduler, that is responsible of scheduling the entire job provided by the user to the operating system. And the second one is the process schedule. In reality, we actually know that there are many jobs and many processes that will compete with each other for the computer resources, including the memory, including the hard disk, and including the CPU. And in order to handle those multiple processes and jobs, we know that the process manager is responsible of facilitating the schedule of processes and jobs in an efficient way. For that being said, the process manager would use a queue. So a queue is where we have this data structure that facilitates first in, first out. So if we do have process 1 comes first, process 2, process 3, process 4, and process 5, and then you would like to execute the processes in the order they have arrived. This is if you do have non-priority queue, for example. So first process that should be executed is process 1, followed by process 2, followed by process 3. But we need to create a queue. In lab 1, you should be able to design a queue, and you should be able to process multiple processes arriving in order, and then store them in a queue and execute them in the order they have arrived. So when we are talking about process manager, we are talking about a job controller. That means we are referring to part of the process manager that is responsible of controlling blocks or of jobs or blocks of processes. And this is a data structure that we will talk about it later, that for every process or a job that will arrive to the system, it is associated with a block. This block has some information about the process or some information about the job. This is a block of the memory that we understand that it will store information about this job or process. We know that once a process arrives and the schedule will decide on which process to be executed based on the information in the process block, we call it a process control block or a job control block. So sometimes we refer to process control block or job control block, which will be stored in a queue instead of the process itself. That means each process will be represented by a process control block. This process control block should be stored in a queue, and then the scheduler, as a part of the process manager, will decide on which process or job should be executed first based on the allocation in the queue. So the main idea behind why do we need to manage the processes is actually to guarantee that we have an efficient synchronization of multiple and different processes with the current available different resources. This is because whenever resources could be used by more than one user or even a single user with multiple processes, we have two issues that we might face, and we have to guarantee that your operating system is capable of solving this issue. The first one is called a deadlock problem. This is where we have only one resource, and then we have multiple processes trying to access those resources. And then this guy would like to have resource one, and let's make it resource one. And then this guy would like to have access to resource, actually has access to resource two, while it requests access to resource one. And this is process one, this is process two. So process one has access to resource one, while it requests to resource two. And then process two, it has access to resource two, while it requests access to resource one. So it's a deadlock. Like process one would like access to resource one, while it has been captured by resource two, and what has been captured by process two, and process two would like to have access to resource one, while it has been captured or acquired by process one. It's a deadlock. I will never have like a situation where it could be resolved and the resources are allocated outside this deadlock. And the second issue that we might see commonly in operating system is called starvation. Starvation means we have multiple resources, for example, and then process one has access to this resource one, process two has access to resource two, and then process three has access to resource three, and each one of them actually holding the resource without releasing it to other processes. That means if I do have process four always starve. It will never have access to any of those resources. That's why we have starvation. The responsibility of a process manager is to solve those two issues. That's why when we design an operating system, we would like to design component of the operating system that manages the memory efficiently. We would like to design another part of the operating system as a process manager that schedules the processes efficiently and handle any issues related to deadlocks and starvation, for example. And we're going to talk about this also in details in later classes. The third manager, this is not related to the memory nor to the scheduling of processes or the management of processes. This is the input-output manager, which we call it the device manager. So the input-output manager, which is responsible for accessing to the input and output devices. We know that in reality, there is a limitation on the number and the speed of the input-output devices in a computer system. And because these devices are slower in speed as actually compared to the CPU and the memory, when a process would access an input-output device, the device is not available to the other processes for a period of time. Which part of the operating system is responsible of an efficient use of those input-output devices? This is where the design of the device manager comes in place. That being said, the responsibilities of a device manager is to monitor every input and output device to ensure that this device is working in a proper way. It is functionally efficient, and to maintain a queue for each input-output device access, or one or more queues for similar input and output devices. And also another responsibility of a device manager is to control the different policies for accessing those input and output. So if there's multiple policy to access input and output, the device manager responsibility, and we're gonna talk about the design of a device manager, how it works also later on, is to provide control of the different policies that will help in accessing the input-output devices. Finally, the file manager. So the last manager as a component or a sub-manager underneath the operating system is the file manager. We know that operating systems nowadays, they use file manager, they control access to the files. Those files could be file systems for the operating system itself, or it could be file systems for the applications provided by the user. But keep in mind, it's a bit tricky because a discussion on a file system would actually require more advanced knowledge of the operating system principles and file access concepts that it's beyond the scope of this textbook, our textbook. In the course, I would go over some fundamentals of file managers at the end of the semester, but I will not dig deeper in this. In general, I just want you to know the responsibility of a file manager would include controlling access to files. So we need file managers to control access to files, to supervise the creation and the deletion of files, to provide a supervision of the modification of the files, as well as the naming of the files, also to store the files for archiving and backups. That's why the operating system should be designed in a way to provide memory management, because without an efficient memory management scheme, we cannot consume or provide allocation to the memory efficiently. We'd like also to have a scheduler or like a process manager that is capable of scheduling which process to be executed. And once we design an efficient scheduler, that means we have efficient allocation to the memory as well, because they interact together. That means the scheduler will decide on which process to allocate it based on the response received from the memory manager. And we do need the device manager, so we know exactly which device is available to be used. We would like to control the access of the devices by which we have an interaction with the device manager, as well as operating system and also the memory manager. And finally, we need the file manager because we are dealing with a lot of files. We are not the primary memory right now. We're talking about the hard disk, for example. So we need the file manager as another component of the operating system that will help in controlling access to the files, including the creation, the deletion, the modification, and also the archiving of those files. So without those four components, we don't have an efficient, sustainable operating system to perform the required tasks and to resolve issues in computer systems. That means for any operating system, at least we should have four components or four managers. So after we covered the different components of an operating systems, let's now dig a little bit deeper into the main structure of an operating system. As I said before, there are three basic elements that would make up the major design component of operating system, whether this is memory management, or is it a process manager, or is it file manager or device manager, we see the operating system as a 3-layer program or a 3-layer software. The first layer is the user interface layer, followed by the kernel file layers and the file management system. So the first component of an operating system, which we refer to as the user interface, we know that each operating system would have a user interface. This user interface would accept those requests or processes that are given by the users, and this interface will interpret them for the rest of the operating system. That means if we have any user, this user will send a request. This request should go to the operating system, but because we cannot just go directly to the shell of the operating system, nor the kernel of the operating system, we do have the user interface. So any request given by the user would be sent to the user interface, and the user interface is responsible of accepting those requests from the users and then interpret them to the rest of the operating systems, which include the shell part and the kernel part. The user interface in some operating systems, for example, like Unix. So if you're referring to the Unix, that's where the shell comes in place. So you would replace the operating system at the shell, while in Windows, you will look into the GUI, or like the graphical user interface component of your operating system. So the second main component of an operating system, we refer to it as the kernel. So every operating system has its own kernel that interact with the application given by the user through the interface and the hardware level. The kernel is the core of the operating system. So every operating system has a kernel that acts as the communication layer between the application through the user interface, as I said, and the hardware. It is the core of the operating system. The kernel is responsible of loading and operating those programs or processes provided by the user or even the system, and also managing input and output. That means in the kernel, we can see process manager. So process manager is part of the kernel. We also can see device manager because it interacts with hardware. So this is the device manager. We can see memory manager. So we do have the memory manager. Memory manager is here. And then the file manager is considered as a different component, not part of the kernel. Kernel acts as the bridge between applications and the actual data processing, which is done at the hardware level. So what else do we know about kernel? We know that the operating system software, which is copied into the RAM from the hard disk drive that's happening during the boot up, this is the kernel part. So what actually being copied from the RAM to, from the hard disk into the RAM, this is during the putting up process, this is the kernel. We know that the kernel remains in RAM while the computer is on and in charge. It is in charge of the overall operation of the computer system. We know that coded inside the kernel, we do have the internal programs of most of the use operation, for example, as copying files. In Linux, we refer to the KMM, and in Microsoft, we do have command.exe. So we have addressed the first layer of operating system as an interface, the second layer, which has the three managers, like the process manager, the device manager, and the memory manager. The last layer is separated as the file management system. The file management system is what actually the operating system used to organize and manage files. So this is a different version of the four managers. So an operating system, when we talked about it before, it has four managers. Those four managers related to processes and memory and device and file. So this is where we talked about the four managers of an operating system. If we talked about the layers or the main component or the structure of operating system, we could see it as a user interface, and then a kernel, and then a file management system. A kernel would include the device managing part, the process part, and the memory part. The file management system is a little bit separate when we look to the structure of the operating system. We know that some definitions we should be aware of. What is a file? A file is just a collection of data. What is a file management system? And the system that is required, in which the operating system will use it to organize and manage files. We know that virtually all the information that a computer would store will take a form of a file. There are many different types of files. It could be data files, and it could be text files as well, in addition to some program files. The way an operating system will organize those the information into those files, that's where we call it the file system. So a file system is the architecture or the structure of the organization of the files designed by the operating system. We know that the traditional file system that is commonly used in modern operating system is the hierarchical file system, in which actually files are stored in directories under a tree structure. The starting point or the root point or the beginning of this directory is called the root directory. So after we have talked about the user interface and a kernel and a file management system and how each one of those components works separately, allow me to give you an introduction of what we call it system call. So system call in particular is those high level or like codes that we write it in a C program. That's not a system call. A system call is a call provided by the kernel that is responsible of translating the high level instructions given by the user into a system call that would be executed by the kernel to have a direct access to the hardware. So there are two levels that we might consider on a user level and a kernel level. On a user level, we just see processes. But on the kernel level, like this is the core of the operating system, we see some system calls generated by the operating system to have access to the driver, like like for example, drivers in general, or the scheduled drivers, or even the file system drivers that will be connected, for example, to the screen or to the hard disk. So if we'd like to process what will be given by the users from the user level to the kernel level, the kernel will generate some system calls that will translate what's provided by the user to what would be understandable by the hardware. So if you do have an application given by the user, for example, it's a C program. So if you do have a C program, if you write a C program, I'm sure you're aware of the C, and you write a function called open. So this is on the user mode. On the kernel mode, we need to write a system call. Luckily, it's called open as well. This is by the IEEE standards that will implement the system call. This will have access to a file on the hard disk or an access to the file system, for example, to perform a certain open operation and return it back to the system call interface and then backward to the user application. So why this is happening? Because we know that kernel create and delete processes. It provides direct access to the hardware. The kernel supplies those well-defined system call interface. And we know that application would set up system call arguments, and the kernel perform operation and return the results. So a user, when he or she sends a request, it doesn't go directly to the operating system. It goes through the interface first, and then from the interface to the kernel will translate those user calls or high level functions into system call that will be transmitted to the hardware for execution. So we need a system call interface that takes in place what will be provided by the user to what will be executed by the operating system. So a system call could be defined in one word. We say it's a special instruction transfer that will give a control to the control, which dispatches to one of the few hundred system calls handlers. So in general, in C, you might write a function like printf. The corresponding system call might be write operation. If you do have a function like scanf, the corresponding system call is a read function. So who has put this mapping? It's the standard POSIX for Unix interfaces provided by IEEE standards. So if you do have a function that would need write or printing, you would go to the system called write. And if you have a function that would need to scan or read, you would go to the system called read. That being said, when a user provides a high-level functions, it goes through the system call interface before being sent to the kernel to actually transmit it to a system call provided by the operating system to call the hardware of the system. So let's take another example on this to show how the system call works. So this is your C code. This is the standard C code where you do include some standard library started by your main function, and then you would like to print this message on the screen. When this is your application, and then when you send it to the operating system will scan this, responsible of scheduling the process. It's now in the memory. Now we'd like to execute it. What will happen is on the user mode, we see the printf function. However, in the kernel mode, we were able to call the standard C library, and a system call like the write function has been executed that will have access to the screen or the monitor, and then display the message on the screen, return back the result to the user mode. So we know that the standard library was implemented in terms of number of system calls. This is provided by the IEEE standards, as I said. So any printf that you might see it would have a privilege of writing to the console, for example. It would be easily translated to a system call like the write function. This is done in the kernel component, which will send this to the output serial port to print on the screen, as an example. So what is the standard portable operating system interface? So the portable operating system interface is an interface provided by the Unix IEEE standards for Unix-like operating systems, such that for every reading operation, we do have a standard system call. For every writing operation, we do have a standard writing call. So this is the standard IEEE in all of Unix-like operating systems. So each user write whatever he or she wants as a code, and then we do have one system code corresponding to the code of the user. It has to be standard provided by the portable operating system interface. Recently, Microsoft Windows is fully compliant with this. Also, how many system calls we do have? There are many system calls related to a lot of tasks as connected to the hardware level. So in the POSIX, it's actually a collection for those standards that covers many of those system calls and libraries. The typical one is the POSIX 1003.1, which is related to the C language interface to the Unix-like kernels. And you have to know that while various programming languages, they do actually provide specific mean of access keys, but every POSIX compliant operating system would implement the following basic IOO function. For creating, we have system called create. For opening, we just have one system called open. For closing a file or closing a certain data structure provided. Normally it's related to files. We use a system called as close. We have one system called read and write, and so on. So it's standard. No one can change it as long as it's Unix related. Windows is fully compliant with this. That means write whatever you want as a user, send wherever you want as a user in terms of your application and request. But when it comes to the kernel layer of your operating system, there's only a couple of system calls that we're going to use it per language, or the standards for a certain system call. And then it will be executed based on the type of the system call that has been sent. So what is the shape of the collection of the system calls that are stored, like in particular for the C language? This is what you should expect stored in your operating system. It's just a file that executes the open operation. And it's, as I said, it's typical standard for one system call like the open operation here. This is what would you expect if you're going to write some shell scripting or like language using C programming. So what I have discussed over this class is just an introduction to what is an operating system, where and why do we see operating systems, what type of operating system we might see, how the evolution of the operating system took place, what are the main components of and managers underneath the operating system, what are the main layers and structure of operating system, finally, how a process should be handled when it's sent from a user to an operating system. We guarantee that a system call is generated. So with this is the end of the class. And next week, we're gonna start talking about the first component of operating system. I will start by the process manager, and then over a couple of weeks, we will continue on this topic. And then later on, we will start the next manager, which is the file manager.